Hello friends. So, we discussed about the development of weighted residual statement for 3D elastic continuum, and how do we also looked at how it can be converted into a weak form by taking recourse to Gauss divergence theorem and converting a volume integral into a surface integral, and that leads to the basic boundary element, boundary term of the variable, and from there we can identify the primary variable and the secondary variable. Secondary variables are the tractions, surface tractions, which are the forces, and this is the weighting function. So, that leads us to identification of the primary variable as the unknowns of the problem, 0th order derivative, the same form as the weighting function appears in the boundary term. So, u, v, w, these are the primary variables for 3 dimensional elasticity, and these are the corresponding tractions in x direction, y direction and z direction, and boundary term is a product of these two, which is actually the work quantity. So, from there we found derived this inference that approximate solution for u, v and w, it needs to be continuous in the primary variables u, v and w, and it should have non-vanishing first derivative in the domain, because the highest order of derivative in the weighted residual statement, weak form of weighted residual statement is first order, and first order derivative should exist. So, that implies the choice of finite elements of C0 continuity, that is continuity of the 0th derivative of primary variable across element boundaries, and we will see how that is ensured in our subsequent discussions. And these C0 elements are needed for the discretization of the domain by finite element method. Now, we simplify the problem a little bit. As we discussed, 3 dimensional is of course very general, but it also brings in lot of complexities in visualization, because essentially what we are dealing with is a 2 dimensional medium. The screen is a 2 dimensional medium. We can simulate third dimension through effect of perspectives and all, but it becomes very difficult, very complex visualization. So, it is easier to develop the concepts for simpler geometries in 2 dimensions and develop the finite element approximation for 2 dimensions, and to understand the basic concepts of 2 dimensional elastic continuum, and those concepts can be readily extended to 3 dimensional continuum without any problem. They just extend very logically. So, again for 2 dimensional elastic continuum, the simplifications it can be derived. So, the differential equation of motion, there are only 2 dimensions. So, 2 components x and y. So, these are the differential equation of motion for 2 dimensions. So, del sigma x x by del sigma x del x plus del tau y tau x y by del y plus f x is equal to rho u double dot. So, that is the rate of change of momentum. So, this is essentially Newton's second law, and again in operator notation this can be converted into L transpose d L u plus f is equal to rho u double dot. So, that is in operator form. So, L is the differential operator relating the strains to displacements, and L transpose is the transpose of that operator, and this is what we have for 2 dimensional elasticity, and F is the vector of body force components in x and y direction, and u is a vector of displacements. So, going by the domain residual, so substitution of these approximation, let us say we approximate the solution as u approximated by u hat and v approximated by v hat. U and v are the deformations in along x and y directions respectively, coordinate directions respectively. So, we can substitute these approximations u hat and v hat in the governing differential equation L transpose d L u plus f is equal to rho u double dot, and this is what the domain residuals are in x direction. So, r omega x is this expression, straightforward component wise expansion of that expression, and second one is the residual along y direction, and we can going by the method of weighted residual. So, we can state the statement of weighted residual as multiplied by weighting function this residual and integrated over the domain. So, now domain is of course dx dy. So, that is d omega infinitesimal planar area, and the domain is contained in xy plane, and the third dimension of course is the constant thickness. So, for z direction the problem is assumed to be invariant with respect to z direction. We will discuss little bit more about what happens in z direction, because the body is of course 3 dimensional. It is only that we are ignoring the variations. We are saying that along z direction nothing exciting happens, and under what conditions does that happen and how valid that is, we will see in a short while. So, T refers to the integration with respect to z direction. So, that is the thickness part, and this is taken as unity. T is taken as unity in the case of plane strain problem. So, this is the weighting function and this domain residual and integrated over the domain and equated to 0. So, that is the statement of weighted residual. Now, we can again invoke first we convert this into a total integral by chain rule of differentiation, and then for total integral we will we can invoke the Gauss theorem, and this del over del x that will become direction cosine n x, and this del over del y that will become the direction cosine n y, and so on. So, the weak form then becomes this boundary term W 1 multiplied by this derivative term multiplied by n x. So, that is the traction, and this is the second term del y term. So, that becomes n y direction cosine n y, and this is the boundary integral taken along the counterclockwise direction. So, the curve, it is a 2 dimensional area, 2 dimensional domain will be bounded by a curve, and now the boundary integral has to be evaluated moving around this curve in counterclockwise direction, and this is of course T thickness. And the second term, the boundary weak form. So, the derivative gets transferred to the weighting function del W 1 by del x, and similarly del W 1 by del y, and so this is one weak form of the domain residual in x direction, and this is the weak form of the domain residual in y direction. So, 2 equations, and there are 2 boundary terms in these 2 equations, and looking at these boundary terms we can identify what are the primary variables and secondary variables. So, W 1, so this is 0th order derivative. So, substituting the unknown corresponding unknown of the problem. So, that is u along x direction. So, primary variable will be u displacement along x direction, and the secondary variable is the traction along x direction. Similarly, looking at this second equation W 2, that will be again 0th order derivative, and so the primary variable will be v, the displacement along y direction, and this secondary variable, corresponding secondary variable will be the forces along y direction. So, this is how when I said if planar area bounded by curves. So, it can be assembly of straight lines or it can be a smooth curve, whatever. So, in case of finite elements we will be looking at these kind of regular geometry. So, this is the outward normal for each of the edges and the boundary integral is evaluated moving in the counterclockwise direction along this path. So, counterclockwise direction of evaluation of boundary integral in two dimensional domain, and the primary variables are displacements u and v, and the corresponding secondary variables, these are the tractions of forces which are given by sigma x x n x, that is direction cosine of the outward normal with respect to coordinate directions x and y. So, n x is direction cosine between n and x, n y is the direction cosine between n and y, and similarly T y tau x y n x plus sigma y y n y. So, now looking at this term boundary term and this identification of primary variable and secondary variable, we can draw the similar inferences like what we had discussed in the case of 3 dimensional problems. Let me repeat, the approximate solution needs to be continuous in the primary variables with non vanishing first derivative of the primary variables in the domain. So, this non vanishing first derivative comes from here. So, these are all first derivative terms in the domain. So, del u hat by del x, del v hat by del y, del v hat by del x, del u hat by del y, and similarly here in the first equation. So, the first derivative should exist and the weighting function it has to be also have a first order derivative non vanishing. So, we consider finite element discretization by C0 continuous elements of 2 dimension that is required. So, what do we mean by finite element discretization by C0 continuous elements? So, again you can get some idea about the kind of elements that we might have, some kind of this plane geometry with enclosed some area enclosed by very straight lines. So, it can be a triangle, it can be a rectangle and so on, right. So, now let us look at a little bit about what are the assumptions, under what conditions these planar 2 dimensional approximations are valid. There are 2 particular idealizations that we consider. One is called plane strain idealization. In this, as the name suggests, the strain field is limited in one plane, xy plane. So, outside xy plane the strains are 0. So, what are the strains outside this plane? So, epsilon zz direct strain along z direction, the distortions shear strains gamma yz and gamma zx, distortions in yz plane and distortions in zx plane. So, they also vanish, right. So, under certain situations, certain geometric configurations, it can be assumed, I mean these 3 components of strains epsilon zz, gamma yz and gamma zx, they are indeed very small in comparison to other 3 components of strains, that is epsilon xx, epsilon yy and gamma xy. So, when that happens, it is a reasonable approximation to consider these 3 strains to vanish, and then the problem becomes confined to 2 dimensions. The strains are confined to 2 dimensions, that is xy plane. Remember, strain being confined to xy plane does not imply stresses also being confined to xy plane. Sigma zz will be contributed by there will be some contribution to sigma zz coming from the other direct strains. So, epsilon xx and epsilon yy will contribute to sigma zz by virtue of Poisson's ratio. So, by no means epsilon zz is equal to 0 implies sigma zz also 0 nevertheless. So, once we substitute this epsilon these 3 strain components to be 0 in our generalized Hooke's law. So, this D matrix can be appropriately regained, and sigma ZZ you can find that sigma ZZ can be related to epsilon XS and epsilon YY, and it can be taken out of consideration from this equation. So, we can have only 3 components here for stress sigma XX, sigma YY and tau XY, and 3 components of strain epsilon XX, epsilon YY and gamma XY, and because all these 3 terms would vanish. So, these this D matrix will appropriate terms can be picked up from this D matrix, and we can get the constitutive matrix for plane strain cases. And because epsilon ZZ is considered to be 0. So, obviously, the deformation along z direction is also 0. So, the deformation can only be taken as u and v as function of x and y. So, this state of deformation is referred to as plane strain deformation in xy plane, and it is identical at all sections along the length, I mean this z axis body, and the 3 dimensional problem can be reduced to a 2 dimensional analysis of just one cross section, and we look at the cross section and we get the fairly good idea about what is happening where in the body in the entire system. With respect to z, it is the same picture that will keep on repeating for different values of z coordinate. So, that is one idealization. So, if the strains, if we can assume strain to be limited to one plane, normal to the plane, strains to vanish, we can also consider similar kind of arrangement at the other extreme, that stresses are limited to one plane. We are not talking about strains, but the stresses. So, stress normal to the plane, they are 0. So, that means sigma ZZ is 0, tau YZ is 0, tau ZX is also 0. So, again now we are left with 3 stress components, and for these 3 stress components there will be 3 strain components, and again because of Poisson's effect epsilon ZZ will not be 0 in case of plane stress problem, but that can be derived from the knowing the stress and strains in xy plane, we can find out what is the epsilon ZZ. So, at the other extreme we have situation where the domain is bounded by 2 planes and separated by a small distance. We will see what it means, and the bounding surfaces, bounding planes that are there, they are assumed to be stress free and the loading is in plane, right. So, if this is the plane, the loading is in plane, there is no normal direction loading, right. This will violate the, if there is a loading in case of like this normal to the plane, then this violates the plane stress assumption. There is no way we can assume sigma ZZ to be 0 if the loading is along z direction, right. So, if the loading is in plane, so this is xy plane and the loading is also, all the loading is also in xy plane, then this is a valid condition for plane stress idealization. And thickness is of course considered to be very small. So, along the thickness the variation is very small. So, we can assume it to be constant again, right. So, the state of stress becomes sigma xx as a function of xy, sigma yy direct stress, normal stress along y direction is a function of x and y in the xy plane, and then shear stress in xy plane is also varying from point to point in xy plane, and normal to the plane all these stress components are 0. And with this we can again find what is the suitable constitutive matrix, D matrix to relate stresses to strain. That is a very important thing. Plane D matrix for plane strain condition will be different from D matrix for plane stress conditions, right. You can look at this from the during the assignments. So, how do we do this, and you can also look at the various books about finite elements and continuum mechanics. How does the constitutive matrix differ in two cases? I mean, in plane strain case and for plane stress case, how does the D matrix differ in these two cases? Now, coming to the example of plane strain problems and plane stress problems. So, plane strain, this is consider the embankment dam. So, there is a cross section, this is a impervious core, and there is an upstream cross section, and there is a downstream slope, and this is of course impounded reservoir, and this is the downstream flow water level. So, now if you look at it, if you visualize this case, so along z direction it is a very long dam, right, and it is uniform, the loading is uniform, and there is no normal to this plane, it is all embankments, and that is all restrained by the valley. So, there is no other external force acting normal to the plane x y. So, sufficient distance away from the supports where there would be some local influence of the reactions from the valley mountains. This entire thing can be considered as a plane strain problem. This strain normal to this direction epsilon zz will be 0, and of course, the distortions in yz and xz planes, they will also be negligible, and this becomes a very simple, very straightforward idealization for plane strain conditions, and the model can be analyzed. I mean, using plane strain condition, the advantage, why do we need to go into this unnecessary supposedly unnecessary idealization, because it is an idealization. At the end of the day, epsilon zz is never 0, right, gamma xz, gamma yz is never 0, but we still assume them to be 0 because there is something called curse of dimensionality. We see that as the problem dimensions increase from the 1 dimension to 2 dimension, from 2 dimension to 3 dimension, the number of variables increase dramatically, exponentially. So, the problem size increases tremendously. I mean, if we will see that from 1 dimension problem to 2 dimensional problem, there is a considerable increase in the problem size, and if we introduce the 3rd dimension, then it is a exponential increase, right. So, there is a problem with the capacity of the computers which will be used to solve this problem, because at the end of the day it is the number of simultaneous equations have to be solved by the computer, and if the number of variables becomes very large, then it might very well be possible that the computer may actually not have enough power, computing power to solve that problem. And secondly, this such a voluminous data also becomes very difficult to interpret. It is easy to interpret this 2 dimensional figure, I can see what is happening, I can draw after computation, I can draw stress contours, I can judge what is the where is the where are the zones of stress concentration which needs to be looked at, and what are the potential failure zones, and I need to pay attention to that, and so on, right. So, this 2 dimensional geometry is very helpful in taking those quick calls. Of course, once the design is ready, it is always recommended to have a full 3-dimensional analysis of the system once the design calculations etc. are complete. Based on, I mean, designs are of course for the preliminary designs, when it is undergoing several iterations, cycles of iterations, evolution of design, it is not really worthwhile to spend time into developing a very complex 3-dimensional mesh, and if the design is to be revised, so why bother. So, that way 2-dimensional idealizations are very simple and very quick, and we can get very useful design parameters, very useful estimates for the design parameters, which can be helpful for refining the designs. And once the design is finalized, then of course, the final analysis as a check is done using 3-dimensional discretization. So, this is of course embankment dam. So, the normal to the plane z direction dimension is very large, so that epsilon zz becomes very small. I mean, epsilon zz, what is epsilon zz? Change in length divided by the original length. Original length is so large, change in length deformation becomes very small compared to the original length. So, epsilon zz is small, and similarly for the distortions. Compared to this plane strain, this is the cantilever bracket problem that is very common in industrial setups. So, this is we can see that it is a very thin kind of a structure, thickness, very small thickness, and it is taking a in plane load out of the plane. It is completely stress free, and since the thickness is small, the state is not going to change much across that thickness. So, this problem is idealized as a plane stress problem, and again we consider the stress distributions in xy plane, and then after the analysis we can find out what are the stress contours and different stress contours, and look at zones of concern wherever the stresses are higher than acceptable limit, then something needs to be done to revise the design. So, these kind of idealizations, these kind of 2-dimensional idealizations make it very easy to visualize the results and interpret the results, and that is why they are very popular, very commonly used in design offices for when the design is still evolving. And the computer programs can be written very quickly without much of complication. For same element, same finite elements can be used to model both plane strain and plane stress problems. There is another class of problems which can be which are again 3-dimensional, but which have axisymmetric, which are symmetric about an axis. So, those are what we call as solids of revolution. So, again in that case if we model the problem using cylindrical coordinates, then it is again the cross section, we only need to worry about cross section, because along the theta direction there is no change because of symmetry of the problem. So, there is no variation with respect to theta direction, right. So, like this pen, so this is a solid of revolution, it is all whichever value of theta we take, cross section we take, it is the same behavior. So, we only need to look at what happens within that particular cross section, and the picture will remain same at whatever angle we look at. So, again the same elements, plane strain, plane stress elements, they can be used as axisymmetric elements as well, except that the domain integrals they have this 2 pi r factor coming in instead of theta, because in the third dimension instead of z it is the theta direction and the circumference has to be taken care of. So, that would be 2 pi r. So, we will not discuss axisymmetric problems in this discussion. they are very there is a very small difference, as I said, only t is replaced by 2 pi r and rest of the things are similar. So, you can refer to the books on finite element to look at axisymmetric problems, but we will the bottom line remains that in all these three cases, plane strain, plane stress and axisymmetric, the finite element approximation is only in xy plane within one plane, and that is what we are going to discuss. How do we construct finite element approximation and how do we establish the finite element equilibrium equations and then assemble those to develop a global system of equations, and which can be solved for primary variables, the nodal displacements, and subsequently they can be used for post processing to derive the stresses and the stress contours, and for subsequent analysis for the stress resultants. So, we will continue with this finite element, the characteristics that need to be adhered to. How do we construct finite element approximation in 2 dimensions in our next lecture. Thank you.